Hi, this is Mr. Mac. This is a concept video on trigonometric identities. In your textbook, it's chapter 14, section 1. Now, we want to start out with, once again, definitions of the basic trigonometric functions. So if we have some angle theta and a line segment that's the terminal ray, and at the end point we've got the point xy, and we allow the length of this line segment to be considered r, then we can define the sine of theta to be y over r, the cosine of theta to be x over r, the tangent of theta to be y over x. Now what we want to do is we want to take a look at different ways of writing the same thing. These are called identities. Now, an identity is a very important thing because it's something that's true for all values of theta. So with these definitions, if we can show that it's true when theta is just a variable angle, then it'll be true for all values of theta. Now, some of these things are really fairly obvious. Others of them become kind of surprising. So let's kind of go through a list of some things here. So imagine, first of all, that we had the expression sine of theta divided by the cosine of theta. Now, according to the definition, that would be y over r divided by x over r. And you know that if you're dividing a fraction by a fraction, you flip the second fraction and multiply. So that would be the same thing as y over r times r over x. But the r's would actually cross cancel and we're left with y over x. But if we look over here, look at what y over x is equal to. So we can say this is equal to the tangent of theta. Now this is a pretty important identity. It seems kind of simple, but the first identity we would like you to know is that the sine of theta over the cosine of theta is equivalent to the tangent of theta. Now we can also go with a couple of other things. You were told that the cosecant of theta, I can do this, the cosecant of theta was the reciprocal of the sine of theta. So that's 1 over the sine of theta. And so the sine of theta is equal to 1 over the cosecant of theta. We're going to do the same thing with the secant of theta. Secant of theta is equal to 1 over the cosine of theta. And the tangent of theta, let's keep this kind of, the cotangent of theta is equal to 1 over the tangent of theta. These are what we call ordinarily the reciprocal identities. Those are really pretty obvious. And so let's go on to something that's a little bit more exciting. Now, if we were to take a look at the expression cosine squared of theta plus sine squared of theta. Now, I need to probably stop here for just a moment and let you and talk to you a little bit about this expression here. See, it says cosine squared of theta. Now what that really means is you take the cosine of theta and then you square that value. When you see a cosine squared of theta, what that means is you take the cosine of theta and then you square it. But this is the way everybody's kind of used to seeing it. You do need to take care, though, that this exponent of 2 really looks like an exponent, because we do have an expression that's the cosine of 2 theta. Now what this means is you multiply theta by 2 and then you take the cosine of it. These are two very different things. They are not equal. So don't get them mixed up and don't write them so that it's confusing to a teacher as to which one you mean. I promise you, if you write cosine squared of theta and I can't really tell whether it's a squared theta, cosine squared of theta or cosine of 2 theta, I'll just mark it wrong and I'll believe that it's the wrong thing. So be careful with that. Penmanship counts here, honestly. So now that we know the cosine squared of theta means you take the cosine of theta and square it, the cosine of theta is defined to be x over r. And so we could just say the cosine squared of theta is the same thing as x over r squared. And the sine of theta we know to be y over r. So we could say the sine squared of theta was y over r squared. Now, obviously, that makes x squared over r squared plus y squared over r squared. But when you're adding fractions with the same denominator, you add the numerators, keep the denominator. So that becomes x squared plus y squared over r squared. Now let's just stop for a moment and look back here at our original diagram. Notice we have the point xy, we have the radius r, and if we were to actually look at this, the point xy, the x value would be this distance here, and the y value would be this distance here. And x, y, and r form a right triangle where r is the hypotenuse and x and y are the two legs. But that would mean the Pythagorean theorem applies, and the truth would be that x squared plus y squared would be equal to r squared. But look at this. We have x squared plus y squared on the top, and we have r squared on the bottom of this expression, and we know that those two expressions are equal, and anything over itself is 1. So the cosine squared of theta plus the sine squared of theta is equal to 1. Now, we call this the Pythagorean identity. It's a very important identity, first of all, and secondly, the reason it's called the Pythagorean identity is because it comes from the truth of the Pythagorean theorem. The cosine squared of theta plus the sine squared of theta is 1. That's a pretty cool identity. It's one that you should remember. And see, the cool thing about this is it works no matter what the value of theta is. It's always true. Now, there are a couple of things that we could do to this identity to make it look a little different. So let's go ahead and take a look at a couple of those things and see if we can't investigate the Pythagorean identity a little bit more. Now, see, if I were to take this identity and divide both sides by, just spitballing here, the cosine squared of theta. So I have cosine squared theta plus sine squared theta divided by cosine squared theta equals 1 divided by cosine squared theta. What would actually happen? Well, first of all, on this side, we could rewrite this as the cosine squared of theta divided by the cosine squared of theta plus the sine squared of theta divided by the cosine squared of theta equals 1 over the cosine squared of theta. And algebraically, I'm sure that you realize this is the same as cosine theta over cosine theta squared, and this is sine theta over cosine theta squared, and this is 1 over the cosine theta squared. But what is the cosine theta over the cosine theta? Well, it's 1, right? And if we square 1, we still get 1. Now, what is the sine of theta over the cosine of theta? Here, let's just have a finger pointer here, and let's go up and see if we can't find an identity for the sine of theta over the cosine of theta. Look at that. It's equal to the tangent of theta. So we can say tan of theta, and that's being squared. So let's just put the squared here, tan squared theta. Now, what is 1 over the cosine of theta? Well, 1 over the cosine of theta turns out to be equal to the secant of theta. So we get on this side the secant of theta, and it's being squared, so we'll just put a squared here. So we could say 1 plus tan squared theta equals the secant squared theta. And this is what we would call the second Pythagorean identity. It also comes from the Pythagorean theorem because it came from the first Pythagorean identity, but this is a kind of an important one to know also. Now, if you divide both sides of this identity by the sine squared of theta, you end up with 1 plus the cotan squared of theta equals the cosecant squared of theta. I'm not going to take a lot of time doing that one, but this is what we would call the third Pythagorean identities. So there's 3 Pythagorean identities, and guys, a lot of you are all the time asking me, do I need to memorize this? And guys, I cannot imagine being successful in trigonometry without knowing these 3 at least. So yes, you do need to memorize these. It's a good thing that you saw where they come from, but still, you do need to memorize them. All right, the next thing we want to take stock of is what is called the co-function identities. Now, let's take a look at sine of 90 degrees minus theta. Okay, now I'm going to go back and appeal to the trigonometric or the right triangle concept of SOHCAHTOA. If we have a right triangle, and let's let this be theta right here, then this would be y, this would be x, and this would be r. And we know that the sine of theta would be y over r, and the cosine of theta would be x over r. Now, there is a theorem in geometry that says in any right triangle, the two acute angles are complementary. So this angle right here, oh, by the way, that's a really poor joke. Let me tell it to you. What is the definition of a complementary angle? And the answer is, well, a complementary angle is one that goes to another angle and says, hey, you're an acute angle. That's a complementary angle. I know it's pretty bad. But anyway, this angle right up here, the one that I started to draw the arrow, is actually the complement of theta. So it would be 90 minus theta. Now, if we use 90 minus theta as our angle, then the opposite side to 90 minus theta would be x, and the hypotenuse is always, of course, r. So the sine of 90 minus theta would be x over r, but that's the same thing as the cosine of theta. And the adjacent side to 90 minus theta would be y, so the cosine of 90 minus theta would be y over r, but that's actually the sine of theta. So the cosine of 90 minus theta is the sine of theta, and the sine of 90 minus theta is the cosine of theta. These two identities right here are the co-function identity. Well, actually, there's one more. There's the tangent. So let's take a look at that one. We know that the tangent of 90 minus theta is equal to, from an identity we did a little bit earlier, the sine of 90 minus theta over the cosine of 90 minus theta. But we know from these identities right here that the sine of 90 minus theta is the cosine of theta. And we know that the cosine of 90 minus theta, by these two identities right here, is the sine of theta. And from earlier, we found that the cosine of theta over the sine of theta was another way of writing the cotangent of theta. So we have the sine of 90 minus theta is equal to the cosine of theta. We have the cosine of 90 minus theta is equal to the sine of theta. And we have the tan of 90 minus theta is equal to the cotangent of theta. And of course, the cotangent of 90 theta will be equal to the tangent theta as well. Those are the co-function identities, and that's kind of an important thing. Now, one thing I'd like to just say here is that one of the things that students have a tendency to do, which is a mistake, is they distribute the trigonometric function over the binomial. Now, you cannot do that. This is not sine of theta times 90 minus theta. This is the sine of 90 minus theta. The sine is a function. We're taking the sine of the angle 90 minus theta, and that is not equal to the sine of 90 minus the sine of theta. So don't do that. If you do that, you are guaranteed to get the wrong answer. All right. Now, we want to talk about negative signs as well. All right. Now, these, I may just go ahead and give you these. The sine of the opposite of theta is equal to the opposite of the sine of theta. The cosine of the opposite of theta is equal to the cosine of theta. And the tangent of the opposite of theta is equal to the opposite of the tangent of theta. Now, what this means is that the sine is what we call an odd function. You see, an odd function is one that when you take the negative of if you take the functional value of the negative of an input, you get the negative of the functional value of the input. So notice that an odd function takes the negative sign you're taking, the negative sign you're taking the sign of, and passes it through. That makes it odd, okay? The cosine gobbles up the negative sign. It just says the cosine of the opposite of theta, same thing as the cosine of theta. Now, that makes the cosine an even function. Now, we did take a look at odd and even functions a little bit earlier in the year, and that had to do with polynomials and exponents on polynomials and so forth. But the basic concept of what the function does with the negative sign is still intact. See, the sine of the opposite of theta becomes the opposite of the sine of theta. The cosine of the opposite of theta just becomes the cosine of theta. Cosine is even, sine is odd. Now, it turns out the tangent passes the negative sign through too. So think about it for a moment. Yes, the tangent is also an odd function. In fact, it's kind of important to know that of the 6 basic trigonometric functions, sine, cosine, tangent, cosecant, secant, and cotangent, let's see, the sine, tangent, cosecant, and cosecant are odd functions, and only the cosine and the secant are even functions. And it should make sense, since the cosine is even, its reciprocal function is also even. The other ones are all odd functions. Now, that is a basic rendition of the trig identities. Once you get to trigonometry, you'll probably spend more, or pre-calculus, probably spend more time doing a lot of things with trig identities, but this is the foundation for all of the other stuff we do. Now, the one thing that I'm seeing in our book, and also in the end of course exam review, is questions like this. They'll say something like, okay, the sine of theta is equal to 5/13, and theta is in, say, the second quadrant. Now, a lot of times they say theta is in the second quadrant by saying something like pi over 2 is less than theta is less than pi. And in radian measure, remember, from 0 to pi over 2 is in the first quadrant, from pi over 2 to pi is in the second quadrant, from pi to 3 pi over 2 is in the third quadrant, and from 3 pi over 2 to 2 pi is in the fourth quadrant. Remember, in fact, let me just go ahead and write this in. 0 less than x less than pi over 2, pi over 2 less than x less than pi, pi less than x less than 3 pi over 2, and 3 pi over 2 less than x less than 2 pi. Remember, the radian measure is the arc length on the unit circle, and if you have a unit circle, in other words, a circle with a radius of 1, the circumference is 2 pi, so if you start here and travel around the circle, you would expect to have traveled 2 pi units. So what we're being told here is, paraphrase of this, is theta is in the second quadrant. I'll just write here quadrant II, or second quadrant. Now, what we should do then is we just go ahead and draw an angle that's in the second quadrant. We'll call this theta. And then this angle right here is theta ref, the reference angle. And this would be the right triangle we're looking at. Now, since the sine of theta, or theta ref, is 5/13, we would have a 5 here and a 13 here. Because remember, the sine is y over r, and r is the hypotenuse, and y is the up and down line segment. Now, we can use the Pythagorean theorem to find this length right here. So if you square 13, you should get 5 squared plus, let's just call it x squared. So 169 equals 25 plus x squared. Now subtract 25 from each side, you get 144 equals x squared. And now we're going to take the square root of both sides. That means x is equal to plus or minus the square root of 144. Now I hope you know that the square root of 144 is 12. If you don't, you'd ask your calculator and it would tell you. Now the plus or minus is important this time because we're in the xy plane, and it's important to know whether this distance is a positive distance or a negative distance. So from the origin out to this point right here, it would be negative 12, right? Now, the question they will ask is, what is cosine of theta? Well, now that we look at it, the cosine of theta is actually going to be the cosine of theta reference angle in this quadrant. So that would be the adjacent over the hypotenuse. We get negative 12/13. Now, there is another way to do this using the trig identities. We do know that sine squared theta plus cosine squared theta is equal to 1. And since they told us that the sine of theta was 5/13, we could write 5/13 squared plus cosine squared theta is equal to 1. Now 5/13 squared is 25 over 169. To solve for the cosine of theta, we would subtract 25 over 169 from each side. We get cosine squared of theta is equal to, now I just want to say 144 over 169, but think about it with me. 1 is the same thing as 169 over 169, and when we're subtracting 25 over 169 from 169 over 169, we get the same denominator, 169, and the numerator is 169 minus 25, which is 144. Now, when we take the square root of both sides, we have cosine of theta is equal to plus or minus 12/13. Now, since they told us that the cosine was in the second quadrant, remember, the cosine is related to x, so in the second quadrant, it would be negative. And so there we would say the cosine of theta was equal to negative 12/13. Now, it's nice, I think, that we get the same answer both ways. Let's just do one more thing. What if they said, instead of what is the cosine of theta, they said, what is the tan of theta? Well, then we could go back over here and look at this again. Now, the tan of theta is y, oops, okay, the tan of theta is y over x, so we would get 5 over negative 12, or negative 5/12 for the tangent of theta. All right, now that's a rather significant foray into the trigonometric identities, and here we are doing all of it in Algebra 2. Hopefully you'll get a chance to see it more and do it again, but this will take care of what we need for this year. And we're done.